I wanted a geometry problem, and it's been a little while since I've done one of Katrina's geometry problems, so I chose this one. As always, big props to Katrina for making these, and thank you for letting me use them. Like we normally see with Katrina's problems, the beauty is kind of in the simplicity of it. What you see is what you get. We have 3 regular hexagons, 2 of which are congruent, the third of which has an area of 10. And the question is just to figure out the area of the triangle pictured. And what I want to do is present 2 different ways to solve this problem. One that just uses brute force, and then one that's much simpler and more clever, but it's a little bit easier to see after you've already done the brute force method. However, for either method, it's pretty hard just to get started. Maybe I could provide one little hint that would allow people that want to tackle this on their own before they watch my solutions.
Define a constant to represent the length of the sides of the small equilateral triangle bounded by the hexagons.
It's pretty hard to see, but the triangle that Hector was talking about is this little guy. So maybe we label the sides T for triangle. Now I think we're all set up to solve this guy, so let's start with the brute force method. Since we know the area of the red hexagon is 10, we could figure out the length of the sides of the red hexagon. And while there's formulas for such things, in case you don't have the formula memorized, all you gotta do is think about this hexagon as 6 equilateral triangles. The area of a triangle is half the base times the height, so the area of 6 equilateral triangles is 3 times the base times the height. The base is just the length of the side that we're trying to figure out. And the height, if you don't want to use trig, can be written in terms of the length of the base, because since we're dealing with equilateral triangles, the length of the base is the same as the maximal radius of the hexagon, which is why I'm representing the length of the base with the capital R. Using Pythagorean theorem, the sum of the square of the length of the legs of the right triangle is equal to the square of the length of the hypotenuse. You know, a squared plus b squared equals c squared. So we can solve algebraically for h to get that the height is root 3 over 2 times r. Substitute that into our area equation to get an equation with just one variable, r. So we solve that equation for r to find what we were looking for, the length of a side of the red hexagon. We can now solve for s, the length of a side of a blue hexagon, by focusing on 2 specific blue sides, which coincide nicely with red sides. If we focus on these horizontal lines, we see that r plus t equals s. And if we rotate this red edge about this vertex, the diagonal lines imply that 2r equals s plus t. So we have 2 equations, and since we already have a value for r, there are only 2 unknowns, s and t, so we can solve for s, the length of a side of the blue hexagon. After doing so, we're in pretty good shape. Remember, our goal is to find the area of this triangle. The area of a triangle is half the base times the height. The base is just s, the length of a side of the blue hexagon. So if we could figure out the height of this triangle, we'd be done. We'll know that the height is just the distance kind of across 2 of these hexagons. In other words, 4 times the height of one of the equilateral triangles that make up the hexagons. As we saw earlier, the height of an equilateral triangle is root 3 over 2 times the length of a side of that triangle. So the height of one of our blue equilateral triangles is root 3 over 2 times s, and therefore the height of our yellow triangle is 4 times root 3 over 2 times s. If we plug in our expression for s, we get this huge mess, which we can simplify by first canceling out a 4 and 2 2's in the denominator, and then noting that we have the square root of 20 root 3 squared. The square root of any amount squared is just that amount, so that's just 20 root 3. The product of the 2 square roots of 3 is just 3. 20 times 3 is 60. 60 divided by 4 is 15. So that works, I guess. I mean, one way to solve this is definitely brute force. I don't know how satisfying or fun it is, but it works. 15 is definitely the right answer. But wouldn't it be cool if there was a way to solve it without doing all that algebra? Like never calculate any side lengths at all? Turns out you can. Remember about 1 minute and 40 seconds ago when we noticed a relationship between some side lengths, which produced 2 equations that we solved to figure out that s was equal to 3/2 of r? Because the hexagons are similar, when we scale the sides by a factor of 3/2, we scale the area by a factor of 3/2 squared, or 9/4. That means the area of a blue hexagon is 90/4. And since the hexagon is made up of 6 equilateral triangles, the area of each equilateral triangle is a sixth of 90/4, in other words, 15/4. And it'll turn out that we can use the area of the blue equilateral triangle to figure out the area of the yellow triangle that we're looking for. And that might be a little bit surprising, as the triangles clearly aren't similar. And not only is the yellow triangle not equilateral, it's not even isosceles, nor is it a right triangle. But none of that will matter. Note that the 2 triangles share the same base. And since the area of a triangle is just half the base times the height, if we could relate together their heights, we could relate together their areas. Well, as we saw earlier, the height of the yellow triangle is just 4 times the height of the blue triangle. So since the base is consistent between the two triangles, the area of the yellow triangle is just going to be 4 times the area of the blue triangle. 4 times 15/4 tells us that the area of the yellow triangle is just 15. The same answer we got earlier with a lot less algebraic manipulation. As always, I'll end the video with a challenge question. In the original diagram, what portion of the area of this hexagon does not lie within the bounds of the yellow triangle? And in the spirit of this video, if you're feeling clever, can you answer this question without actually calculating the area of the blue hexagon nor the area of the yellow triangle? Feel free to share any thoughts, questions, or solutions in the comments.